Hi and welcome to this video on bias and variance in machine learning models. I am Raghavendra, an expert in AI, ML and data engineering. By the end of this video, you will be able to recall about evaluating machine learning models, list the types of prediction errors, detail about bias and variance, and explain how to obtain the ideal values for bias and variance for getting best predictions. So, to understand bias and variance, it's important to first understand about model evaluation. Model evaluation is expressing mathematically the performance of a trained machine learning model, which is achieved over any given data. A supervised machine learning technique is one where the labeled data is used to build the model. The machine learning model's performance is measured based on how correctly the model predicts on an independent test dataset. The test dataset used to make predictions is assumed to be completely different from the dataset used to train the model. The model learns the parameters from the trained dataset and generalizes it on an independent unseen test dataset. If the predictions made by the machine learning model is incorrect, we call that as an error. In simple terms, the difference between the actual values and the predicted value is called as an error, or in other terms, it's called as prediction error. Now, let's try to understand about what are prediction errors in more detail. Prediction error is a summation of two parameters, irreducible error and reducible error. Irreducible errors are errors which are beyond the control of an algorithm or the dataset. Irrespective of a particular algorithm or the parameters to the algorithms, these errors cannot be reduced. These errors are caused by an unknown factor that may be influencing the predictions. Moving on to reducible error. Reducible error has two components, bias and variance. Let's now understand each of these terms in more detail. Bias measures as to how far are the predicted values from the actual values. High bias is when the average predicted values are far off from the actual values. The reason for high bias could be due to the fact that the model is too simple and does not capture the complexity of the training data. In simple terms, bias is due to ineffective training, also called as underfitting. Increasing the complexity of the model might help improve the trained model, which in turn improves the bias. Let's look at the other reasons for bias. Lack of richness in the dataset. Let's assume that in the prediction of a marketing campaign of an e-commerce site, if one happens to use the dataset from last year's marketing campaign, again, that is a reason for which could be a reason for bias. Although in the first look, it looks harmless if the dataset in the past was collected for women accessories and now if it is used for men's clothing. The bias in the dataset cannot be corrected. Second reason is based on heavily imputed data. If the data has undergone heavy cleaning and is filled with regressed data for the missing value specifically, there would probably be a bias in the model. The third reason for bias is this. This could probably be based on the synthetically generated data. If for the lack of availability of large data, and if the data is suppose synthetically generated by numerical distributions, the mathematical trend will impose a bias in the constructed model. So these are the reasons probably which could be the reasons for bias. Let's move on in understanding about variance. Variance occurs when the model performs well on the training data set, but it does not perform well on an unseen data or on the test data set. A model with high variance becomes heavily tuned to the training data. When such models encounters a different unseen data point which it has not learned, fails to make a correct prediction. High variance results in something called as overfitting of the model, where the performance on the test data set is below par with the performance of the model on the training data set. Let's now understand how the increase in complexity of the model impacts the error terms of bias and variance. In the context of decision trees, entropy or information gain plays a vital role in the construction of decision trees. A tree is constructed by splitting the data point based on a feature with the highest information gain. When a simplest decision tree is modeled with a depth of the tree which is as small as 1, it expresses high inefficiency in model training, resulting in high bias. The accuracy of such a model will be really bad on both training and on the unseen test dataset. Such a scenario of inefficient training resulting in a very high bias is called as underfitting. When the depth of the tree is increased, the bias reduces, which in turn improves the model training. If the depth of the tree is increased such that the tree grows to the maximum limit where every sample is split into a single node of the tree, in such high depth trees resulting in almost single digit samples in each node for a binary class, the tree is very specific to the training samples, resulting in a training loss of almost 0. This indicates that the bias is almost 0. Such trees are very specific to the training samples and would be unable to generalize and hence unable to make predictions on the unseen test data set. And this is a classical case of overfitting. Now, having learned about bias and variance with the case of decision trees, let's move on to look at a very important concept, which is a trade-off between the bias and the variance. Models with low complexity are easy to train, but results in high bias. As we increase the complexity, like for example in the case of decision trees where we allow the tree to grow to a maximum possible depth, the bias however decreases but results in a high variance. We need to choose an ideal value for the depth of the tree such that it results in an optimal value for bias and variance. It is very easy to say that the model is undertrained and it will not perform better as it did not learn anything. Such models express high bias and high variance. But as the model gets trained to the data with a slow increase in the complexity, after a certain point, the model loses its performance. When it starts to overfit, finding the sweet spot in this trade-off is often quoted as bias-variance trade-off. Let's now understand bias and variance in the context of regression. In linear regression, we fit a straight line which is closest to all the data points, and it's impossible to get a straight line which passes through all the data points. The straight line, which we also call as the predictor line, is at a very minimum deviation from the training data points. This results in the bias of a trained linear regression model. Suppose instead of a straight line, we fit a polynomial curve. The curve now passes through almost all the data points. As we increase the order of the polynomial curve, it exactly fits the data points of the training set, and the bias in this case is almost 0. Now, the model is so very tuned to the training set that it perfectly fits the training data with no deviation or no bias, but fails to generalize on an unseen data, resulting in overfitting. To summarize, here we build a complex regression model and put a polynomial curve instead of a straight line to reduce the bias. It ultimately results in overfitting. As the polynomial order of the curve increases, the model gets additional degrees of freedom to be too faithful to the training data, and thereby missing to produce a performance on an unseen data, and thus becoming very sensitive to minor changes to the input, and hence resulting in a higher variance, low bias model. Here are the key takeaways from this video. Prediction errors can be either reducible or irreducible errors. Reducible errors are expressed as bias and variance. In low complex model, the bias is high and the variance is also high, and the model needs more training and needs to be tuned further, which results in underfitting. As the model gets complex, in the sweet spot results in low variance and low bias, and this is the idealistic scenario. In the model where the complexity is too high, it results in low bias and high variance, resulting in overfitting. Thanks for watching this video.